Assalamualaikum. Good morning, Dr. Nurdini, and also good morning, Dr. Nurdiana binti Nurdin. Welcome to our UI Creates program.
Morning.
Good morning. Waalaikumsalam warahmatullahi
Yeah.
Yeah.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome back to the UI Creates 2024. First of all, let's say thanks to Allah Subhanahu wa Ta'ala, who has been giving us happiness, health, and mercy, so we can attend in this event today. Salawat and salam always be delivered to our prophet Muhammad Sallallahu Alaihi Wasallam, who has guided us from the darkness until the brightness like now. The Honorable Lecturer and all of participants, thank you very much on your present and active participation since day one, and we hope that the same energy for today's session. Today, we will continue on our lecture about heterocyclic chemistry and its role in drug discovery or medicinal chemistry with Ibu Dr. Engineering Nurdiana bin Nurdin, and will be moderated by Bapak Dr. Bayu Ardiansyah, SSI MSI. Bapak Dr. Bayu Ardiansyah, SSI MSI, is a lecturer at Chemistry Department, Universitas Indonesia. He has research interests at synthesis organic chemistry and natural product chemistry. He got bachelor and master degree from Chemistry Department, Universitas Indonesia. He got PhD degree from Chemistry Department, Nara Institute of Science and Technology, Japan. He had many science publications, one of them about synthesis and bioactivity of coumarin, coumarin-chalcone, and chalcone-triazole molecular hybrids. Ladies and gentlemen, I will give time to our moderator, Bapak Dr. Bayu Ardiansyah, SSI MSI. To Bapak Dr. Bayu Ardiansyah, SSI MSI, time is yours.
Okay, thank you very much, Miss Hilna, for the kind introduction. And good morning, Dr. Insinyur Nurdiana binti Nurdin, Dr. Nurdini Muhammad Saleh, and participants of this UI Creates online program 2024. Today we perform the lecture session 7 with the topic of the heterocyclic chemistry and its role in drug discovery. Okay, as we have seen that in our previous lecture series that highlighting the importance of the synthetic and also natural product chemistry in drug discovery. So today we will have the very important presentation, very important lecture about the heterocyclic chemistry from the prominent lecturer, Dr. Engineer Nurdiana binti Nurdin from Chemistry Department of University Malaya. Before we start the lecture session, I'd like to say thank you very much to Dr. Nurdiana binti Nurdin for your kind cooperation and your contribution to this UI Create Lecture Series program. And I'd like to introduce Dr. Nurdiana binti Nurdin to all of you. Maybe for you guys, those from chemistry department of UM, Dr. Nurdiana maybe is familiar in and also your lecturer, yeah. But from student for student from Universitas Indonesia, maybe this is your first time to meet virtually Dr. Nurdiana, and I'd like to introduce her. Dr. Nurdiana, as you can see in the screen, has academic qualification. She got the bachelor and master degree program from University Malaya, and then got the PhD doctoral degree in the physical chemistry area from Karlsruhe University of German. And she has research interests in the area of microfluidic devices, biohydrogel, including thin film, aero and ionogel, and also the advanced topic in the nuclear magnetic resonance research topic, including diffusion, kinetic multiple enzymatic reaction, and para-hydrogen. Dr. Nurdiana binti Nurdin has many articles in the reputed international journals. Too many if I read one by one here, but I would like to highlight maybe one or two publication. Her recent publication in journal Food Composition and Analysis, entitled "The Current Method for Peroxide Detection in Food and the Emerging Role of Heteroaromatic Dyes as an Efficient Alternative." And also in journal Chem Photochem by Wiley publisher, Dr. Nurdiana and her coworker published the title "Effect of Fluorination on the Properties of 9,9 sulfonyl bis compounds as host for thermally activated delayed fluorescence emitter." Yeah, very many publication she has. Okay, please continue. And then not only journal article, but also Dr. Nurdiana is highly active in writing books. For example, the books Monitoring Organic Synthesis via Density Functional Theory. This is the recent project by Dr. Nurdiana. So many project previous and also ongoing research project. For example, as co-researcher in the year of 2023 until 2025, chromatic catalyst unleash anthraquinone derivatives as potent dye precursor for peroxide value detection in oily gastronomic delights. So that is just a piece of her research experience and research interest, and also she has many publication and also books in a reputed international publisher. So we are very lucky to have Dr. Nurdiana come and available as our lecturer in the UI Create program. Okay, so without further ado, I would like to give the time to Dr. Nurdiana binti Nurdin to give her the important lecture, and I hope that the student can participate actively during the lecture session, and also please open your camera, because opening camera and actively participate in the lecture and also discussion session will be used for the complete attendance assessment for UI Creates participant. So I'd like to give the time to Dr. Nurdiana. Assalamualaikum, Dr. Nurdiana.
Waalaikumsalam warahmatullah. Thank you for very kind introductions.
Yeah, Dr.
Okay.
Nurdiana.
So, should I start first, or how the program, the arrangement of the program?
Okay, yeah, you can start for maybe around 1 hour, 1 hour more. Yeah, it's up to your prepared material, but at the end of the lecture, maybe please spare the time for the question and answer session, and also if possible maybe little bit exercise or delivering or the homework question. Yeah, Chris. Yeah.
Okay. All right. So maybe I should share my screen first. Cool. So everyone can see it?
Yes, Doctor.
All right. Thank you. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good morning to everyone. And first of all, I would like to thank our moderator, Dr. Bayu. Thank you for very nice introductions. So those that still, those that doesn't know me yet, my name is Dr. Diana. Okay, I'm basically recently, not kind of recently, just like almost 3 years already that I joined University Malaya for as a senior lecturer, and my field basically physical organic chemistry, but I was assigned in the organic sections team. So I had experience in terms of organic synthesis and computational chemistry during my master. And then when I pursue my PhD, so basically it's shifted a bit towards the physical chemistry. To be exact, it would be the mechanical engineering, because I need to develop some of the NMR coil, the probe, and then build my own microfluidic device that integrate with the microdetector NMR, and then grow a gel there, and then attach with the enzymes. So it's kind of like multidisciplinary things. So basically, I would say that I had a little bit of experience in terms of organic things, physical chemistry things, biology, physics, and also some engineering part. Okay, without a few further, so let's continue with our, continue for the topics about lecture series 7, heterocyclic chemistry and its role in drug discovery, medicinal chemistry. So basically, when we talk about medicinal chemistry. So when you go to the pharmacies, okay, let's say you buy lotions or you buy some vitamins, right? You tend, I'm not sure, for me, for my case, I tend to look at the ingredients. When I look at the ingredients behind the things that you like, for example, lotions, you tend to see some of the chemicals. You found some chemicals on that ingredients, right? So when you search, you search into the Google, and then you will see almost of these ingredients contains heterocyclic compounds. So what are heterocyclic compounds actually? So when we talk about heterocyclic compounds, it's actually a cyclic compounds that contains at least one atom that is not a carbon in the ring. So for example, in that molecule in the ring contains, for example, nitrogen, oxygens, and also some sulfur, and some others heterocyclic in that ring. Okay, so common heterocycles usually when we see, we have indole, we have pyrrole, we have pyridine, benzofuran, benzothiophene. Okay, so there are some importance and applications for these heterocycles. So for example, the important is in Malaysia or in Indonesia or even in Asia country, there are so many plants. When you try to extract the plants, you tend to see some heterocyclic compounds. Like there are some also that alkaloid compounds. So these alkaloid compounds contain some indole or pyrrole. Okay? We are going to see this later on in specific. But just for the introductions here, I just want to make sure you guys know what are heterocyclic compounds and what are the importance and what is the applications. So for example, the applications obviously for this lecture is about the medicinal chemistry. So it means that when you have the compounds of the heterocyclic compounds, that you can do some medicines for the treatments later on. Okay, and also it's also this compound used for the agrochemicals and some of the material science. So this can I just move this? Oh, Entschuldigung. Oh no. Just want to cool. Okay, so I just want to share you this table for the classifications of heterocyclic compounds. You have saturated and you have saturated and you have also unsaturated. Okay. So saturated means that you don't have any pi bonds. I mean, it's just a sigma bond between C to N and also C to C, something like that. So, and another one is unsaturated compound. So unsaturated compound contain pi orbital. And heteroatom also, you can do some 3-membered heterocyclic compounds, 4-membered heterocyclic compounds, 5-membered, and also 6-membered heterocyclic compounds. So here, the difference, saturated and unsaturated, for example, when we take a look at 3-membered heterocyclic compounds, you have aziridine, you have oxirane, and you have sulfur. So this one SON, it means that the heteroatom that embed in the ring. And this, for the unsaturated, you can see that C double bond N, C double bond C here, and then C double bond C here. Okay, you cannot do C double bond O here, because then the ring is not stable. All right. So this is the classifications of the heterocyclic. So in my case, I mean, in my topic, I will focus on 5-membered heterocyclic compounds, because there are so many heterocyclic compounds, and I don't think I managed to go through all of them. Okay, so I just pick 5-member heterocyclic compounds, and we will see the reactivity on that 5-member heterocyclic compounds, and also the where these compounds comes from, the natural sources or the synthetic compound, right? So before that, this 5-member heterocyclic with one heteroatom, we need to see the characteristic on aromaticities. For example, like pyrrole, okay? So we have pyrrole that contains 6 pi electrons. So these 6 pi electrons is basically, this 6 pi electrons is basically an electron excessive, because it rich with the electron in that ring system. So the electron density on each ring atom is greater than 1. Okay, so when you have lone pair electrons, these lone pair electrons inside the pyrrole will take part in the delocalizations. So why pyrrole is an electron excessive aromatic heterocycle? Because when we take a look at the structure of pyrrole, okay, so this is a pyrrole, by the way. So this pyrrole contain electron density on each ring, okay, is greater than 1. What it means by 1 here, because 1 is the dipole moment, okay? So you have here more than 1, here also more than 1, more than 1, more than 1, slightly more than 1, and also this, and H here is more than 1. So pyrrole, the total systems of this pyrrole contain a dipole moment that give a value 1.55 d by, okay? So it's a similar with the pyrrolidine, which is the saturated one. So this one is the unsaturated. Okay, this one is the saturated 5-member heterocyclic. Okay, so when you have the saturated one, the dipole moment is also similar with that number, which is you get 1.57. The only thing is that the dipole moment vector is totally different. It's totally opposite from the unsaturated one, which is a pyrrole, and the saturated one, which is the pyrrolidine. So when you have, what it means by the directions of that dipole moment is actually show you a pointing from the positive charge to the negative charge. So here you can see that it's pointing up, right? When it's pointing up, it means that the positive charge to the negative charge is going from down to the top. So same case, I mean, inversely with this pyrrolidine, where the negative charge go down to the the positive charge go down to the negative charge. All right, and then when we try to compare the different atom of the 5-membered heterocyclic compound, for example, you have oxygens, and then you have nitrogen, and you have sulfur, and also you have carbon here. You can see that the what we call it, the Pauling's electronegativity is increases, okay, when you have more electronegativity atoms that embed with that heterocyclic compounds. So you don't have fluorine here. So usually when you see the polyelectronegativity, it means that it tends to attract the electrons more. Okay, so the increasing of the polyelectronegativity is starting from this furan, and then go to the pyrrole, and then you have the thiophene, and then you will go the aromatic, the aromatic one, right? So this is basically is how the characteristic on the aromaticity of the heterocyclic for 5-membered ring. Next, when we take a look at the electron density for pyrrole, okay, you see that this pyrrole contain electron lone pair that can be delocalized in the in the p systems of the ring. So same case for the thiophene, you have also sulfur that contain lone pair that can be delocalized in the p systems. And also same case with the furan. Furan also has the oxygens which has electron lone pair that can be delocalized in the p system. So the thing is, for this spiral case, the activity, the electron densities is affected more on the resonance instead of the inductive effect. So when you have when you have this and it tends to resonance, I mean, when you have the lone pair from the end here, it tends to resonance on the ring, okay? But for case thiophene and furan, the inductive effect is moreover, the inductive effect for furan and thiophene was a stronger force than their resonance effects, because it tends to it can give to donate the electrons to the other I mean out from the ring. But here the delocalizations of the end is inside the ring, so that the resonant effects is more stronger compared to the inductive effect. So when we take a look at the when you have, let's say if you want to react with some additions, right, electrophilic additions, the heteroatom for this spiral case is actually does not happen, because like I said, the lone pair of the nitrogen here will be resonance, and then you will see that the resonance is inside the ring. So when you have the lone pair that delocalize to the ring, and then you will see that the tautomeric is the resonance effect of the pyrrole is inside the ring, so that there will be no possible to there will be no possible for the electrophilic additions to happen for this pyrrole case. Okay, so this is when we take a look at pyrrole. So there will be another substitutions will happen. We will take a look at the reactivity after this. It's just like to give you some idea about the electron density for the pyrrole systems, how these pyrrole systems actually affects towards on this resonance. I mean, the resonance effect give a very powerful force in that aromatic systems. Okay. All right. Then we take a look at the acidity and the basicity. So for this case, this one, cyclopentane, pyrrolidine is under saturated ring. Okay, but comparisons is between heterocyclic compound and non-heterocyclic compound. So cyclopentane is not this cyclopentane is not heterocyclic compound, but pyrrolidine is a heterocyclic compound. When you take a look at the acidity, okay, sorry, yeah, the acidity. So it tends to give you the pKa almost similar with the pKa. Cyclopentane is almost similar with the pKa of the pyrrolidine. Another one case, you have unsaturated one. All right, for this unsaturated one, is again cyclopentadiene and with the pyrrole. And then you can see that this pyrrole and cyclopentadiene is a bit more acidic compared to this, compared to the saturated one. So what you need to, how we can determine whether this one is more base and this one is more acid? When you have pyrrole and you react in base, okay, so this base will take hydrogen here and then give negative charge to this nitrogen. Okay, so pyrrole actually has a similar pKa value as alcohol. So when you treat it with a strong base, it will convert to its anion. So it means that this one is more acidic, so that when you treat with the base will be easily to extract the proton from the pyrrole. And if you have two different conditions when you want to treat when you want to treat the pyrrole, for example, you have sodium hydride with the TS chloride here, all right? So this TS chloride here does not, when you have sodium hydride, this sodium hydride will abstract the hydrogen here, right? So this sodium hydride will abstract the hydrogen here to give an ion. But this anion, together with the TS chloride here, is just give you a salt. This one from negative charge and this one is from positive charge. It's an ionic bond. Compare to the one that very strong base, okay? When you have this base abstract the N here to give N minus, and then N minus here will attack the C double bond O here and then kill out the Cl. Then you will get the Cl. So basically, you will see that this one is under covalent one, but this one is just like this one. Yeah, it's actually the same. Sorry, wait let me. So you will get the same case, which is the this one hydride. This hydride will this hydride will abstract the hydrogen here, and then it give you the negative ion. So the negative ion will take the TS and then kick out the Cl, and then you will get the NTS. Okay, so this is basically how you determine your pyrrole. So you know that your pyrrole is actually slightly acidic, that can treat with the basics. When you treat with the basics, and then it will give you some products. Okay, all right. So next, let's see the comparisons of the basicity, purity, and pyrrole. Now, when we have aromatic pyridine and we have pyrrole. So this one, when you try to when you add with the acidic one, because we want to study which one is more basic. So we treat with the acid. When we treat to the acid, you can see that the positive charge on N is the pyridinium here has a pKa of 5.2. When you treat pyrrole with the acidic, you will get the pyrrolium, but this pyrrolium give the pKa 0.4. So when we compare the pKa of this pyridinium and this pyrrolium, all right, you can see that is a very huge difference that we can distinguish which one is basic, which one is acidic, right? So for pyridinium here, you will see that it's more so the aromatic for the pyridine actually is more basic compared to the pyrrole. Why? The reason is, the nitrogen lone pair inside the pyrrole ring here, okay, contain the aromatic sextet of the ring. So less available for forming new bonding to an available proton. So what it tends to give you is actually the nitrogen, the lone pair of the nitrogen in pyrrole is delocalized on the aromatic systems. Okay, but for the N here, cannot be delocalized, so it tends to it can be denoted, the proton here can be denoted so that you will get the product, and then so that is the comparisons between the pyridinium and pyrrolium. Okay, so in a simple way, you can say that this pyrrole, the nitrogen of the pyrrole, is actually is less available to form new bond because the lone pair is delocalized on that system, the one that we just see from the electron densities. Okay, so that is the comparisons between the basicity of pyridine and pyrrole. So pyridine is more basic compared to the pyrrole. All right, now we take a look at the sources of the pyrrole and indole. So what is indole now? So pyrrole, you have this one. For indole, you have bicyclic one. Okay, so this one is the indole, and this one is the pyrrole. Okay, so for pyrrole case, the natural product usually coming from the marine sources inside the sea, and then you will see some, I'm not sure what kind of, you see this one? Okay, so this is, when you extract it, you will get some alkaloids compound. So this alkaloids compound contains some pyrrole that you need to extract multiple steps, and until you will get the pyrrole compounds. For indole case, which is this one, usually coming from the vegetables that you eat, if you like vegetables such as broccoli, cabbage, cauliflower, then you tend to have indole inside your body systems, right? Okay, so another one way, that one is coming from the natural sources. Another one way is we can do some synthesize the compounds. We go to the lab, we add reagents A plus reagent B to get the desired product that you want. It's not simple as is that. Okay, so pyrrole usually, the synthetic route is coming from the 3+2 cycloadditions reactions of this compound, TOS MIC, with some electron deficient olefins that we also say it as a Van Leusen pyrrole synthesis. Okay, so this is the name of the persons that tried to synthesis, that discover to synthesis the pyrrole based on 3+2 cycloadditions. And then for the indoles, there are so many name of the reactions, type of the reactions that you can use to synthesis this indoles compound. For example, you have Bartoli reactions, Hermitsberger reactions, Bieshler reactions, Euler reactions, Larock reactions, Nenetzisu reactions, Mandelung reactions, Rysett reactions, and also Fischer-Indole synthesis. So I'm sure that you're familiar with the Fischer reactions, Fischer synthesis, because this one till this one is somehow from the other researcher that try to synthesize this indole compound for certain medicines applications. So when they discover the new procedures or experiments or mechanisms, so they tend to give their own name for the reactions because they're the one that discover the things. Okay. Now, you know already the heterocyclic 5-member ring. You have pyrrole, you have indole, and then you know some electron density, basicity, the acidity of this pyrrole. Okay. So now, when we talk about drug discovery, it means that how from this heterocyclic member can be drug. So the researcher, they are trying to do when they extract the compounds, pyrrole compounds or indole compounds, and then they tend to do some modifications on that compounds, and then they study about what kind of drug for that products suitable for. So for example, like here we have pyrroles. So pyrroles, the derivatives of pyrrole, it's not the pyrrole. Pyrrole is just the parent molecule. So there are some derivative of pyrroles that attach on that ring so that it acts as a, for example, like antimycobacterial, antiviral, anticoccidal, anti-inflammatory, anticonvulsant, antipsychotic, anti-cancer, antifungal, and antibacterial. There are actually some more of the treatments that researchers tends to do, but I just listed some of this only. Okay, and then we have indoles. For these indoles, indoles case also similar like pyrrole, where the researcher try to add some of the functional groups to modify the indoles to get some indoles derivatives, and then it turns out that it tend to give some different drug treatments. For example, we have anti-Alzheimer, anti-Parkinson's, anti-asthmatic, anti-protozoal, anti-diabetic, anti-cancer, anti-anxiety, anti-fungal, antioxidant, and also so many more. And then another examples for benzofuran. Benzofuran, the derivatives, when we take a look at the discovery in drug, benzofuran derivatives tends to give you anti-ulcer, anti-Alzheimer, enzyme inhibitor, enzyme activator, receptor agonist and antagonist, anti-cancer, antiviral, and anti-tubercular. And then we have benzothiophene. So for these benzothiophene, the derivatives, it gives you antimalarial, antifungal, anti-leishmanial, antibacterial, anti-cancer as well. Okay, so far, before I go to the reactivity of pyrrole and indole ring, any questions to raise? Any questions? Any questions 1? Any questions 2? Any questions 3? Okay, so I don't know whether you guys really understand what I'm saying, or you guys just go on with the rhythm. Anyway, let's take a look at the reactivity of pyrrole and indole ring. So when we have pyrrole, first of all, we have pyrrole, and then this pyrrole give you delocalizations from the end lone pair, all right? And then it will protonate. Okay, this is in the scope of protonations, okay? The reactivity of pyrroles and indole ring, we will take a look at first the protonations. So when you have protonations here, the pyrrole, the lone pair from the pyrrole delocalize, and then will protonate the proton here, and then you will get the hydrogens that protonate. So you will get two different products. Okay, first is major product, second is minor product. For the major product, you will see that 80% of that major product contain the proton at C2 positions. Another 20%, the protonations happen at C3. Okay, so this one is C2, this one is C3. So, and inside the pyrrole is actually a weak base. So the value of this base is negative. The pKa of the pyrrole is negative 3.8. So it loses its aromaticity when protonate because the lone pair is part of the aromatic structure. Like I said previously, the N lone pair is delocalized on the ring. Okay, but somehow because it's protonate, now it loses the aromaticity and it will attack the proton, the acidic protons there. So when this kind of reactions exposed to a very strong acid like sulfuric acid, you will tend to have two different product at two different positions. You have C2 positions, which give you a major product, and the second one will be the minor product that give you 20% at C3 positions. Okay. For indole case, indole has 10 pi electrons, so making it aromatic and electron rich. When these electrons are more delocalized, it will decrease the it will decrease the reactivity. When you have when this N protonate, okay, so the indole that you will get, the protonated, so the most positions where the protonated happen will occur at C3 positions, and then it will form the 3-indolium ion. So this is the 3-indolium ion, this one. All right, and then when it forms this 3-indolium ion, so there is no more aromaticity in that ring anymore. So when you have this, so then once you have this intermediates, it can go to further reactions where you get these oligomerizations. So that is the difference between pyrrole and indoles. So pyrrole, it tends to give you C2, which is a major product, but indole actually it give you the C3, which is for your for the major product. Okay, and then you have C2 electrophilic substitutions. For pyrrole case, C2 electrophilic substitutions at position C2. So you will see the lone pair of N here delocalize, and then take the electrophile, then the electrophile go to the positions at C2, okay, and then you can delocalize the positive charge on N here, okay, and then you will get this one. So then if you go to this one, and then you will get positive charge at these positions. So this one, C2 electrophilic substitution, the predominance will be at predominates on these C2 electrophilic substitutions. For C3 case, same here, but you can see that the to stabilize the positive charge here is only one position. So you take the positive charge here, and then you get the positive charge here. So this one, there is no resonance to stabilize the positive charge. So the more you can stabilize the positive charge in the ring, it means that the more reactivity will occur. So here, the notes that I put, so N1 substitution is less likely since the positive charge is localized on the nitrogen. C2 substitution is favor over C3 because the intermediate is more delocalized. So this one, the intermediate is more delocalized. Then protonation mostly happen at C2, showing a preference for delocalizations. Because the more delocalizations happen in that ring, the more reactivity of that compound, so that it will protonate mostly at that positions. Okay. All right. Next, we have C2 electrophilic substitutions for halogenations. Just now, we take a look at the protonations, and then we take a look at the, no. We take a look at the C2 electrophilic substitutions. Now, we take a look at the halogenations. For the halogenations, when you have pyrrole here, the lone pair of N here, delocalize, okay? And then abstract the bromine, then what we call it, oh my God. And then the bond is break, and then you will get this. You will get this product. So take a look at here. You have two bromine that attack on the C2 positions. So let's say if you want to have only one, okay, one side, only one side for the bromine. So you have to control this to become as 1 to 1. So if you have bromine two side, it means that the molar ratio that you use is 1 to 2. Okay? So this is basically, we play around with the stoichiometric reaction. Then you have we have another example here. Let's say you have derivative. You have derivative of the pyrrole here, right? Then there will be some Br. So Br, since you have two positions of the C2 kan. Here, one is here, another one is here. So the right side is already taken by other derivative. So you have only one chance to attack the C2 positions. So then you will tend to get the Br on the C2 positions. But since you have the bulky one, okay, the bulky of the derivative, okay, then it will tend to give you another Br group at the C3 positions. This is when you play with the molar ratio of the reagent 1 with the reagent 2, okay? Let's say if the limiting reagent will be the bromine, okay, the bromine gas, and then you tend to get only one side from the for the C2 positions. But because it's a bromine gas, right? So you have some you have molecules when you have the molar ratio 1 to 2 is the molar ratio 1 to 2, then it will tends to give you at the C3 position as well, because you cannot take at these positions due to steric hindrance. And then here is already taken by other derivative. Okay. And then there will be some exceptions for this rule. When your pyrrole contains some derivative with the bulky group, for example, here you have tips, okay, this one, the T-butyl dimethyl halide. And then what will happen will be, when you have two equivalent of NBS, it will take the C3 positions up here and up here. But if you have only 1-to-1 ratio, it will give you only one side of the bromine for this game. So this happened at C3 positions due to the bulky group that attach on that nitrogens here. Okay. So that is the halogenations for the pyrrole. Then we have Manish reactions. For these Manish reactions, you can see that. So first of all, Manish reactions is a three-component organic reactions that involve adding an amine or ammonia to an acidic proton next to a carbonyl group using formaldehyde. So you have formaldehyde here, and then you have amine as well, and also you have your pyrrole. Okay, so that there will be three components organics. Okay, now how you know that this is a Manish reactions? You already know that because of these three component organic compounds. Okay, first of all, you need to activate the what we call it as a Asian-Moses salt. So Asian-Moses salt here is coming from the trimethylamine here, which is this one. Okay, attack the formaldehyde, and then to give you, so the lone pair of these amine attack the formaldehyde, and then protonate the hydrogens here, and then you will get, so basically this one protonate first because of is in acidic proton, kan? I mean, is near to the acidic proton. So you have this one, this case, this end, attack C double bond O here, neutralize the positive charge, and then you get the alcohol. Okay, and then what happened is now you protonate the oxygen, the alcohol, and then the lone pair from the amine here, remove the water. Okay, kick out the water, and then you get the salts here. So here, dehydrations happen. Okay, and then you will get the Asian-Moses salt. So from these Asian-Moses salts, now you can take these salts so that this pyrrole will delocalize the lone pair of the end, and then attack the carbon here, and then delocalize and stabilize the salt, and then you will get the intermediate of pyrrolidinium here, the positive charge of the end here. And then after that, you can just abstract the H. So who abstract the H here is coming from the water. So that water, extract the hydrogen here, and then give back to delocalize and stabilize the charge, and then you will get the product. So this is the step for the Manish reactions. Well, first of all, you have to activate the Asian-Moses salts from the amine, attack the formaldehyde, and then this formaldehyde protonate. And then one is protonate, you stabilize it, you will get the alcohol. From this alcohol, you then again protonate, and then after that, you need to arrange back from the lone pair of the end so that you can kick out the water, and then you will get the Asian-Moses salts. And then after that, your pyrrole will take an actions to react with the Asian-Moses salts to get the desired product. Okay, okay? Okay. All right. So yeah, so this is the tip where you need to activate the step first. All right. Okay. Next, let's take a look at the real applications, which is germicide. So this germicide is and antibacterial that you can find in the like, for example, this antiseptic germicide bottle, or in the Dettol. You can try to look at the germicide. So how we want to synthesize these germicides is basically based on these Manish reactions. So for example, here you have so these salts compounds react with this reagent with the reactions conditions 20 minutes. Oh, only 20 minutes for at the room temperature. Okay, so you get this 47%, and then you will get the product. The second product, I mean the first product, sorry, the first product. So this first product further react with the formamide and the amine in base conditions, and then you will get germicide. So what is the mechanisms? So the Manish reactions mechanisms actually starts from here. Sini, here to here. Okay, so first you have to activate this one. Activate to give the salt, Asian Moses salt. And then after that, when you get this Asian Moses salt, then you can react with this and here, okay? And then with the salts. You can try to do by yourself, because the mechanisms that I've shown for previous slide is actually similar. It's just the different in the compound, but the concept is there. You just need to try by your own, okay? Okay. Any questions? No question, yes. Oh, I'm talking with myself. Oh wait, there is a chat here. Oh, it's the attendance. I mean, if you have any questions, please do interrupt me, and also you can just write it in the chat box, okay? All right, so if there is no questions, I can just continue. Next, we have Wilshmeyer-Heck reactions. You need to remember, this is under pyrrole. Still, we are talking about pyrrole at C2 electrophilic substitutions. But at C2 electrophilic substitutions, you have so many reactions: protonations, halogenations, what else? Wilshmeyer-Heck reactions and Manish reactions, okay? So for these Wilshmeyer-Heck reactions, it used chloroiminium salt. Just now is you have Asian moisture salt, but now you need to activate the chloroiminium salt. So this is the keyword. So this salt is actually a very weak electrophile, okay, making it very effective with electron-rich carbocycles and also heterocycles. Because of this pyrrole is very electron-rich, so then it will be easily to undergo for these reactions. Okay, take a look at the example here. You have this derivative of pyrrole, and then with reaction conditions DMF, POCl3, and this dichloroethene, okay? And then first you need to activate the salt. You have amine. So this amine, the lone pair of the N here, delocalize and then attack the P, kick out the chlorine here. So that you have the conjugations between these two reagents. So you get this salt, but this salt is not stabilized. Yeah, it's still not stabilized again. So what you need to do, DCl minus attack the carbon bond of imine here, and then you neutralize the nitrogen. When it's neutralized, now you can kick out the POCl2 because POCl2 is good living group compared to chlorine. If let's say if you add chlorine and then here and here you want to kick out the chlorine back, so there is no point why you add chlorine. Okay, so that's why when you have POCl2 here, so this POCl2 is a very good living group compared to the Cl. So once Cl enter to the mechanisms, to the reactions, and then the lone pair of the N kick out the POCl2. Then you will get the Wilschmeyer-Heck reagent. So you just activate the Wilschmeyer-Heck reagent. You did not yet to react this Wilschmeyer-Heck reagent with the pyrrole. Okay. Now, once you have the Wilschmeyer-Heck reagent, you can just start with pyrrole, same C2 positions, right? So N lone pair, delocalize, and then attack the C double bond N here to stabilize the nitrogen. Then you will get the positive charge on the N inside the pyrrole ring. So what you need to do, you have to stabilize the positive charge in the pyrrole. So you take the POCl2, the one that you kick out from the activate step. So this one abstract the hydrogen, and then you can delocalize and stabilize the charge. When you stabilize the charge, okay, you can see that you will get a very you will get the product here, but this product can be further react intramolecular because we have lone pair that activate here. So this lone pair give to the C double bond N and then kick out the Cl, and then you will get the positive charge of the amine because you take already the lone pair. Now you need to stabilize the positive charge here. So how to stabilize it? You add water. Okay, so this water in aqueous will attack the C double bond N here, the imine bond, and then stabilize the positive charge on the N here. All right, so then now step here till here is missing one step. So you can see actually when this one the water attacks the double bond N, you actually get something like this. Okay, there will be arrangement where when this one we go to here, you see there is a H here. This H actually coming from hydrogen here. Okay, so when you have that, so you have this one again. Now, okay, and then this one we take to here because there will be arrangement where this H. Now, when you have this, you should like this. Wait. So you will have sorry, there will be H here. So this one will take and here positive charge and then we'll give back here. So this one actually go to here. So not this one, huh? Not this one, but this one. Okay, so you have, take a look at here. Okay, nampak tak? Okay, so now from this side actually, then water attacks the double bond N here, and then it will give you the positive charge, kan? You can see, right? So water attacks the double bond N, and then C double bond N neutralize the N positive charge here. Then you actually get this one. Okay, so this one you did not get, but you can just directly go to this one. Okay, so you have O, H, and then N. This lone pair N will abstract hydrogen from the water, the one that just entered to the one that just entered, and then stabilize the positive charge there. And then after that, you can get the arrangement, something like this, the one that here. Okay, so this is the new arrangement. Now, you can stabilize the product because we have lone pair from the oxygens. Okay, we have lone pair here. So this lone pair delocalize to stabilize the positive charge of N here. So then at the end, you will get the aldehyde at the group here. Okay, and then this one you kick out, you will get plus N M E H. Okay, so you get the product for the last product for this case. This one, the green one, the green box here. Alles klar? Is it clear? Yes? No?
Yes.
Okay, thank you. All right. So take a look at another the applications from Welsh-Meyer-Hack reactions. For example, here you have neurotessin. So these neurotessins, actually, when you synthesize this compound, you need to use these Welsh-Meyer-Hack reactions until you get this product. So basically, you would like to have at this site. So you tend to get this kind of the product here, the drug can be treated as a neuropsychiatric disease like schizophrenia and Parkinson's disease. Okay, so when we take a look at when we talk about neuropsychiatric disease, this must be related with your nerve. I don't know, saraf also in Indonesia. So there will be some in your brains. There is some nerves. So this drug try to stimulate and help in the this Parkinson's disease and also this schizophrenia disease. Okay, you can try to look at the pharmacies and check the ingredients, and you will find out this drug, neurotoxin. All right. Now, we already talked about C2. Now we talk about C3. So C3 electrophilic substitutions usually happen in indole. We talk about pyrrole that happens for the C2 electrophilic substitutions. But now is the indole, the one that fused ring that happen at C3 electrophilic substitutions. So when indole interacts with an electrophile, the lone pair helps to stabilize the transition states, making it easier for the attack to occur at C3. Okay, let's take a look at here. You have lone pair from the pyrrole, okay, and then this lone pair delocalize and then attack at the C3 position, attack the electrophile, attack the electrophile at C3 positions, okay? And then after that, the hydrogen here being abstracted by some base, and then delocalize to stabilize the positive charge of N here. And then you will get the product for the C3 positions, okay? Oops. So when indole is treated with bromine, it only produces 3 bromoindole. So you have lone pair of the N here, okay? Attack the bromine, and then you have only one product of the bromine. There is no more product for the Br here. So it's only happen at C3 substitutions. It's not at C2 substitutions. Oops, it's stuck. Okay. All right. So this kind of reactions actually is similar like Michael additions with nitroethene, ethyl acrylate, and this Weschmeyer reagent that usually occur at the C3 positions. So when we have Michael additions for nitroethene. So you can take a look at this one will happen at C3 positions. And this one also for the Weschmeyer reagent is also happen at C3 positions. So now the question is, how do you write the mechanisms for this Weschmeyer reagent? Is it the same as pyrrole or is not the same? So the concept will be similar. First, you have to activate the Weschmeyer reagent. Once you get the salts, then the indole start to attack the salt at C3 positions. The only difference is the positions for the attack, the substitutions happen. So for this case, it happened at C3 positions, okay? So let's take a look at Michael additions. So when you have Michael additions for indole, now you have vinyl pyrimidine. So this one is your indole. So this indole attack vinyl pyrimidine, and then you will get C3 positions, 65% of the product. And also here, if you react with vinyl pyridine, you will get the vinyl pyridine as derivative for this indole. So this one, the mechanisms will be easy. Okay, so you have N lone pair there. Okay, and then, sorry, lone pair here. Okay, so now you put here, and then this one can attack the here. Okay, so this one go here, and then you will get here positive charge. Now you have this. Now the next will be you have to stabilize the positive charge on this pyrimidine, because you already attack. You have two things that you need to stabilize. First, the nitrogens from the indole, the nitrogen from the indole. The second one, you have to stabilize the pyrimid, the N positive charge at the pyrimidine. So it's a bit tricky, but you have to do it one step, step by step. Okay. So first, you have this one. Let's read the statement here. So an olefin attached to an electron deficient heterocycles, such as pyridine and pyrimidine, can function as a Michael acceptor. So this one is the Michael acceptor. So it means that your indole is the Michael donator, because it's donate the lone pair that coming from the N is donate to this C double bond C, and there will happen some arrangements there. So when indole is heated in acetic acid with vinyl pyridine or vinyl pyrimidine, so C3 electrophilic substitutions will occur. So at the end, you will get the product of adducts. It means that the additions between the Michael donator with the Michael acceptor, which is for your Michael acceptor, this two, the reagent is this vinyl pyrimidine. It's a good homework for you guys to do the mechanism for this case. Okay. All right. Next, we have the treatment of indole and 4-vinylpyridine with sodium metal in the presence of sulfuric acids that leads to the Michael additions for the indole nitrogen. So here, the case. So this one. So for this case, is suddenly attacked from at the back. So how you are going to do, how you are going to activate this first? So you need to make sure that you will get N positive and negative charge. Okay, so from N negative charge, which means the base, the ethanol, will abstract the hydrogen here to give you a negative charge of the indole. Okay, so the ethanol here, so this ethanol is actually act as a base. So this base abstract the hydrogen from the indole, okay, to give negative charge. And then this negative charge can directly attack C double bond C here, and then you will get the additions of Michael here. Okay. So the mechanism will be the same. I mean, it will be similar. It's just the method on you need to make sure that you activate the N negative charge of indole based on this ethanol based on this ethanol. Okay, so this ethanol act as a base. So this base abstract the hydrogen to give negative charge, and then at the end you can just add with this vinyl pyridine. Okay, and then you will get the product. Okay, next we have Suzuki coupling. So for the Suzuki coupling, the reactions between 1-benzyl 5-bromo-indole involve alkylations of 5-bromo-indole with benzyl bromide in THF. So here, So you have NH here, okay? And then when you add benzyl bromide and with the third potassium hydroxide here inside the DMF, you will get this benzyl bromide. Okay, so this one coming from benzyl bromide, right? Br. So here, kick out the bromide, and then you will get the benzyl bromide additions here. Next, B is 4CF3O, this one. Okay, so what happened? This one is coming just to kick out the BR here, and then you can just, okay, it's like this. So first, here is from bromide, benzyl bromide, okay? And then second, you will get this one, is this one, that kick out the BR, all right? And then again, and then next for the C, you have reaction with oxalic chloride and also acid chloride derivative 6. So now you have additions to this oxo acid chloride, okay? So when you have oxo acid chloride here attached, then that one is the pathway C. You see how they are trying to build a drug based on this based on these reactions. You have Suzuki coupling, you have Mikhail additions, Birchmeier-Hack reactions. So they are using all these synthetic pathway to form the desired products that they want. Okay. And then once you get that, okay, from this C, so next you can see that from 5 here is undergo C and D to get COOME here. Okay, you will get attached from C3 positions. And then for the E, just now also coming from at C3 positions, right? Because oxalic chloride, okay? And then here is just undergo, so pathway E. Pathway E is just undergo hydrolysis, okay? And then you will get carboxylic acid. From the acidic carboxylic, you get the from the chloride, from the oxalic chloride here, derivative oxalic chloride, you will get the carboxylic acid. So now the reactions to convert here is actually the same. Right? Potassium, hydroxide, acetone, water, and HCl. So the point why I show you this kind of reactions pathway to let you know that the core will be the indole one. So the indole compounds has some derivatives by Suzuki coupling via managed reactions and some Mikhail additions, so that you will get the product, the product that you want. And then some of the functional groups here is useful for the structure activity relationship later on, because they want to see which functional group give the best activity towards the desired treatments that you would like to do. Okay. Okay, next we have indole for the managed condensations plus Mikhail additions. You have also same case that you need to activate the salt. So here, again, you will see that at C3 positions happen. Oh, wait. Oh, no. Okay, so you will see that at C3 positions happen, okay, NME here, and then this one deprotonate to stabilize the N positive charge, and then you will get the product called as a gramine. So this gramine can be further react. So this gramine can be further react. You delocalize the lone pair of N here, okay, and then there will be because of the N here, the NME2 here, undergo arrangements to get, then you will get some salts here, okay. Then because you want to stabilize the salts, what you need to do, you delocalize from the lone pair of electron, and then you will get double bond here. So double bond here is not stabilized because you have N positive charge. Now the OAC negative charge will attack the C double bond C and then delocalize the bond, and then you can neutralize the N positive charge. At the end, you will get the product for different derivative of indoles via managed condensations and Michael additions. Okay, so this is the mechanisms for these reactions. And then synthesis of AstraZeneca. So AstraZeneca, or we call it as also as the Zafirlukas accolade, okay, is a drug used in treating pulmonary disorders like asthma, functioning by antagonizing the actions of leukotrienes, arachidonic acid metabolites. So to synthesize this compound, C3 electrophilic substitution reactions occurred between 5-nitroindole and benzyl bromide. So in the presence of silver oxide and dioxins. So you have 5-nitroindole and then benzyl bromide, okay, in the presence of silver oxide and dioxin. So N here, you delocalize the electron, and then you attack, you kick out, okay? So you will get the product here. So now this product can be further. So once you get the, from the, okay, once you get the product, I mean, for this product only, for this case. Now you can do some modifications you can do some modifications of these functional groups to further react to get the AstraZeneca. So like I said, modifications of the functional groups is important for the structure activity relationship that can determine the activity of certain disease that you are studying, okay? All right, so you already know about the reactivity of the indole and pyrrole based on some type of reactions. Now, how you would like to know about the constructions of pyrrole and indole ring? There are so many reactions to construct the pyrrole and to construct the indole, but I will take only one examples. Time for that, if to discover everything. So for pyrrole case, we will take a look at the pyrrole synthesis, and for the indole case, we will take a look at the Fischer indole. How from the Fischer indole we get this indole ring. Okay, first take a look at for the pyrrole. Pyrrole synthesis discovered over a century ago. So they use this is actually coming from the Nor synthesis, and this Nor synthesis, they make it a little bit modifications until they get the pyrrole synthesis. So it involves intermolecular condensations for the primary amine with 1,4-diketone to produce pyrrole. So for example, here you have that it's coming from this. Oops. So it's coming from the 1,4 diketone or 1,4 dialdehyde, and then act with the primary amine, and then you will get the cyclic 5-membered cyclic of pyrrole. Okay, so how the mechanism will be, so the amine attack the C double bond O, the carbonyl group, and then this carbonyl group, there will be condensations happen. Okay, once you get this intermediate, okay, when you get these intermediates, now the next thing will be the formations of cyclizations of the ring. You need to do cyclizations. So when you get the cyclizations, then you can do hello?
Yes, we can hear you now.
Yeah.
Yes.
Okay. I think suddenly the line is missing. Okay. I stopped. Which side I saw, by the way? Is the Palnor, right?
Yeah. Yes, it was the Palmar. Yes, just here.
Oh, okay. Thank you. Okay, all right. So this case, for the Palnor pyrosynthesis, it's actually involve 1,4-diketone or 1,4-dialdehyde, okay, with the primary amine. When you have primary amine, attack this carbonyl group, okay, and then you will get the this kind of intermediates. So from these intermediates, you actually can form cyclizations when you have C double bond, when you have lone pair from the end here, that attack the C double bond O here. Okay, and then you will get some OH. So you have 2 OH. Okay, next, what you need to do, you have to do dehydrations to remove the OH so that you will get the C double bond. Okay, and once you have the C double bond here, now the next thing would be you do the same thing at this side. So there will be this one go out, okay, because once you have this one, you already get this one. Oh. Go here, and then this OH will go out. Okay, and then you will get the same. You just get the same how you try to remove the first dehydrations first. All right, so now, once you do the dehydrations at the first, at the alcohol group, then you have to do the second dehydrations for another alcohol group. At the end, you will get the constructions of pyrrole. All right, and same case. Hello? Okay.
We've got you back.
So, all right. So same case, let's say if we have this drug, it's involved the condensations of 1,4-diketone here. So what you can try to do is, because you have amine here, the primary amine. So this primary amine can attack one of the carbonyl group. Okay. And then you will get the product here. So I think it would be very nice if you can try to do your mechanisms by yourself, because it's basically the concept is the same as what I have shown here, right? And then for the Fischer indole, is this one is you need to create indoles from an aryl hydrazone made from aryl hydrazine. So the condition is the acid catalyst, and then the mechanism involves cyclizations. The mechanisms, the full details mechanisms here. So you have aryl hydrazone, okay, undergoes protonations. So you see that it undergoes protonations, and then isomerizations form to the enamine tautomer, tautomer. Okay, and then second, there will be protonated for the enamine. So there will be protonated for the enamine. So undergoes irreversible heterocyclic rearrangement. So you have the rearrangement to breaking the N proton here. Then there will be a 3,3 sigma tropic. Okay. So now the resulting of double imine, well, you have double imine here, C double bond N here, C double bond N here. Re-aromatize the benzene ring to yield an aniline imino. So you will get the anilino with the imine here. Okay, now next is you have to close the ring. So the N lone pair here, attack the C double bond N here, and then you will get the amino indolin. And then lastly is loss of the ammonia, so that you will get the complete aromatizations for the indole. Right? So this is for the Fischer indole. Just now, Palnor is for the pyrrole, but now is the Fischer indole. All right. So, now I finish with the constructions for the pyrrole and indole. Take a look at the current trends in heterocyclic chemistry. So many people tend to use green technologies and green solvents for their pyrrole. For example, you have pyrrole and indole synthesis using microwave irradiation yields higher results, because you want to make sure that you develop the drugs in a very large amounts, right? So you need to find some ideas how to make it in green synthesis for this drug, or green technology that you can adapt to this drug. Okay, so this is a very important for in this field, heterocyclic chemistry field. So that's why many researchers nowadays tends to use microwave irradiations. Somehow it use also enzyme driven cycles to increase the yield and selectivity. But there are some challenges for this trend, because the scalability, that you need to make sure that this what kind of scale that you would like to synthesize the compound. And how about the cost? Somehow when you want to have some very cool technology, the cost is very expensive. Okay. And then there will be some regulatory compliance. So this is basically one of the journals that I just cited for the green technology, where it used deep eutectic solvent to synthesize the pyrrole. The indoles. Okay, so I think it's nice if you like to see further details about this kind of synthesis, the green synthesis, you can just go to this link, right? And then let's go to the case study, the structure activity relationship, which is what we call it as a SAR. For this SAR case, SAR it means that you want to study the activity relationship of the functional group. Okay, so you remember that you try to synthesize the compound, you modified the functional group, you modified the substituents for the core of your pyrrole or your indole. And then this kind of modifications, you need to know the structure activity that involve either you put this functional group, will increase the activity of your mechanisms or the activity of the biological or vice versa. All right. So this is one of the examples how pyrrole, I took it from another journal as well. So this pyrrole, they try to do some modifications to see the different applications of the drugs that they modify. So some of there are so many derivatives there, and these derivatives tends to give you different of anti-cancer, antipsychotic, and there are so many more. Okay, so take a look at anti-cancer agents. For example, we have this drug that based on pyrrole. So if you tend to put the functional group here, so let's say if the functional group here you replace with the methyl ester, okay, it will decrease the activity. But you need to make sure that the drugs that you are dealing here with the enzymes or the protein that is suitable. I mean, what kind, first thing that you need to know, what kind of disease that you would like to study. For example, you want to study the anti-cancer. So cancer, there are so many places that can be cancers. For example, in liver cancers, skin cancers, breast cancers, stomach cancers. So for example, let's say this one is a liver cancer. So for liver cancer, you have protein that is specific towards that kind of for this cancer to against that cancer. So if this drug fit with the proteins, okay, let's say if it bind very good with the protein and then can try to increase the activity there. So now we have to take a look at what are the functional groups, the one that play a major role to try to increase the biological activity. So for example, here is the C2 positions, which is this one, the green one here, the green box here. Let's say if you replace with the methyl ester, then the activity to against the anti-cancer will be lower. So it means that this one you cannot change it. You have to make it, you have to put it as it is and stick with that. And then let's say if you have another functional group. So this functional group is actually essential for the activity to against the cancer. And this one, for the blue one here, if you replace with morpholino ring with phenyl, then it tends to give you decrease the activity. So it means that this tree, the one that I highlighted, you cannot replace it simply. You have to stick it because the activity with that protein is very good. The interactions against the cancers is good because it increases the biological activity. But others derivative, you can try to play and you can try to modify it. Okay, just to check which one is which functional group give higher activity for that case. And there is another example here for the pyrrole as well. If you replace the R here, sorry, at first it has BR. Let's say if you replace BR with another moiety, you have F and O2 CH3, and then it tends to decrease the activity. So it means that BR here is more suitable with that with the binding interactions. Okay, and then here chloro and methoxy group only show good activity. So if you replace BR with the chloro and the methoxy group, then it will give you good activity. So you have to understand. I mean, you need to understand, you need to identify which functional group give you the best activity. All right. So same case with these different things. This is basically the examples, and it's a good knowledge for you to check. I mean, to understand the SAR for the functional group. All right, and then indoors. So for indoors case, you will see that it's also you see that the indoors give you so many applications. The drugs, the what kind of drugs is suitable for what kind of diseases, can, right? So it's like you have, for example, this drug, the indoors drug, can also treat migraine, depressions, hypertensions, inflammations, cancer, asthma, Alzheimer. Okay, and there are so many more. So this is because of what? Because of their specific proteins can bind with that drugs they develop. So when you have this kind of drug that can give increase the biological activity and treats, so it will be good for the treatments. Again, how you know that? So you have to know, I mean, you have to identify the SAR of the indo. So which functional group give the biological activity increase, which one is not. Okay. All right. So strategy to improve SAR. Somehow, like I said, is because of the functional groups. So you need to make sure you need to really good in identifications. Let's say it's either you have to introduce new substituents such as methyl groups, halogen groups, hydroxy groups, basic groups, carboxylic and sulfonic acid groups, thiol, sulfides, and other sulfur groups. So there are some tips here. Introductions of methyl groups usually increase the lipophilicity of the compounds. So it means that when you put long change or methyl change, alkyl change, right, in that kind of, let's say, pyrrole derivative, and then you put a long change, then you need to know that it will increase the lipophilicity of the compound. It means that it will hardly dissolve in water. Okay, but it's good in terms of good insolubility in fat, because in our, let's say, in our skin also we have some fats, and then it will be very good to dissolve in fat. Okay, hydroxy group reduce its water solubility as shown by an increase the value of the partition coefficients. So when you tend to increase the hydroxy group, it means that you tend to give hydrogen bond. It's either hydrogen bond between the drugs itself, or hydrogen bond with the protein or with the specific enzymes that you study. So because of that, it will reduce its water solubility. Okay. And then basic group is increased hydrophilic nature and a lower lipid solubility. So it gives you hydrophilic nature and lower lipid solubility, means that it will not be easy to dissolve in lipid. And thiols are sometimes introduced into a lead structure to improve metal chelation if that is the objective of SAR. So thiols basically for the excretions. Used for the excretions, easy for the excretions, because because somehow you need to understand the dosage of the drugs that enter into your body systems. So you cannot, there is a limit amount, what kind of dosage, what is the therapeutic index that you need to make sure the drug enter to your body. So how you want to excrete how you want to excrete the drug, the excess amount of the drugs, or either that drug just stay inside your body and cannot metabolize anymore. That will be some dangerous, because there will be another effects that might be interrupt on your body systems. So that's why you need to really identify carefully when you when you dealing with the SAR. Okay, so this is the examples for example for methyl groups. If you increase the methyl group, so you see steric hindrance of methyl analog will lack of the activity. Okay, it means that it doesn't mean when you introduce methyl group, it will give you high activity. So this is kind of like a puzzle that you really need to identify carefully whether it's very suitable to put methyl group in your drug derivatives or not. Okay. And another one is a methyl group bound to an aromatic ring or a structure may be metabolized to a carboxylic acid, which can be more easily excreted. So when you put a methyl group, then it will be easily to metabolize and excrete to the excrete from the body. So this is another. So the one is cons, but this one is a pro. So this is the one that I said that you really need to be careful with the identifications for the SAR. And then for the halogen group, the positions of the substitutions can give you either increase the activity or decrease the activity. And also the bulky, for example, the bulky orthochlorine groups impose a conformational restrictions on the structure that probably will increase the activity. So this is how the researchers study when you have conformational restrictions on that bulky for halogens, then it gives you increased activity. But you need to make sure that the activity that they are talking about is the one that the specific disease that they study. It's not all the diseases suitable for this kind of improvement of the SAR. Okay. And for the hydroxy groups, for this kind of drugs, so when you introduce hydroxy group, it provides new hydrogen bonding, which could influence the binding of the analogs to its target site. So it will increase the hydrophilic nature and also lower lipid solubility. And then we have basic group. So this basic group here can form salts in biological media. And then this one have a lower lipophilicity, but an increased water solubility. So because we have the ionic charge, right? I mean, when you introduce the bond, when you introduce the basic group, there will be either a hydrogen bond or there will be either a ionic bond. So when you so this one will increase the binding interactions with the target sites. So at the same time, will increase the water solubility. Then for the carboxylic and sulfonic groups, so this one also give you increase in water but reduce lipid solubility. And then you have carboxylic, less effect on the activity of large molecules. Then sulfonic acid, usually there is no effect, but it's good for the rate of excretions. Means that if you have sulfonic acid in the drug, it will give once it's metabolized inside your body, so it will easily excrete from your body. Okay, so I give you some of the homework, and including the homework that I just gone through from the slides. Okay, I think it would be nice if you can try to do it. It's like your assignments, and then I would like to see your understanding about this lecture topic, lecture 7. And yeah, do you have any questions to ask before I end my sessions and pass it to moderator?
Yeah, thank you very much,
Right.
Dr. Diana, for the very interesting, informative, and very comprehensive lecture about the heterocyclic chemistry. Yeah. For all of us, for we audience, it is very important to understand what Dr. Diana delivered today, because from this presentation, we can learn about how to construct the diverse heterocyclic compounds with unique characteristic of the molecules. For example, how to synthesize the indole structure, how to synthesize the pyridine or pyrrole, for example. Yeah. So basically, from this lecture, you have to get and learn, and yeah, I think many benefit you can you obtain from this presentation, especially about the characteristic of the synthetic methodologies and also the biological significance of each functionality of the heterocycles. So thank you very much, and we come to the question and answer session. So for those who have a question regarding the heterocyclic chemistry topics, please use this time well, because you can interact directly to Dr. Diana. So please, if you have questions. Okay, Adam, please.
All right. For the Suzuki reaction, the CF3 phenol group that attaches onto the bromine for the benzene compound. Is there a specific reason for that one exactly? Yeah, this group here, just up from the benzene.
So
part of
for
the indole.
C3 positions, because this is under indoles, right?
Yeah, but for the
when we have indole, okay, like I said, pyrrole is usually the position, the major substitutions happen at C2. But for the indole, the major substituents happens at C3 because the delocalizations of the positive charge in the indole is less compared to the C2 substituents.
Yes, but for the trifluorine group that's present on the benzene part of the enol, is there a reason for that part? I think she cut out.
Hello, can you hear me?
Yes, you just cut out for
okay.
quite a bit. Yeah.
Yeah, sorry for that.
Sorry.
Yeah, but I think I'm not sure about what happened to this Wi-Fi. Okay, anyway, back to the questions. So you ask regarding the positions, right? Why indole mostly the substituents happen at the C3 positions?
Well, more about the trifluorophenol group that's present from the benzene group, well, benzene section
Sorry,
of the
come again?
The trifluorophenol group that's attached onto the benzene part of the indole. What exactly is the purpose of this group? Or is that just for that specific drug?
You mean, okay, wait.
Yeah, it's just wondering if there's a reason behind it, or
So
if that's
you mean
just for the drug.
This one?
Yes, that group.
Wait. Why it doesn't move? Let me close this one. Okay. So there is, you say that why this trifluoro CO benzyl here, right? Number 5. Why is it attached here?
Yes. why? What's the reason for it exactly? Or if it's just for that specific type of drug?
Oh, okay. So because you see that there is this one can go here. Wait. No, I really cannot hear you.
Can you hear me?
Okay.
Yeah.
So yeah, can you hear me?
Yep, loud and clear. All good.
So because this one, BR is a good living groups. And this one act as a nucleophile. So this nucleophile can attack the BR positions, and then it can give you the derivative on that positions. Can you hear me? Because
Yes. Yes.
okay.
Is that all? Just to get this type of derivative? It could be exchanged for anything, can it? Or is there a reason for that specific group?
It can be what?
Is there a reason for this specific group to replace the bromine, or
No,
no reason at all? It's just
no,
the
no.
replacing group. Yeah.
Yeah, it's just replacing the group there. Exactly.
Okay. All right. Sorry about that.
Okay, thank you for the questions. Is there any other question coming from UM or UI students? Maybe because of the time, maybe I limit for one participant or one question to ask directly to Dr. Diana. Okay, if no more question, I hope that you all students can follow this presentation, this lecture well, and to check your understanding, please don't forget to work on the assignment given by Dr. Diana, and then submit it to us, and then we will send your answer to Dr. Diana for evaluation. Yeah, this is to something like assignment. Yeah, but the most important is to practice, because this topic is so important for designing the new candidate of drugs. Yeah, so this is very important to not only participate in the presentation, but also please consider to answer all the question given by Dr. Diana. Okay, maybe because of the time limitation, I will close this lecture session today. Again, thank you very much for Dr. Diana for interesting and comprehensive lectures, and I hope all participants will can absorb the knowledge from the Dr. Diana. Okay, from my side, thank you very much, and see you again in the next lecture. I give time back to Miss Hilna to continue this program. Okay, thank you very much, Dr. Diana, and all participants.
Thank you. Thank you so much. Anything you can just email me. All right. Thank you. Have a nice day, everyone. Assalamualaikum.
Have a nice day, Doctor.
Thank you very much for our moderator, Bapak Dr. Bayu Ardiansyah, SSI MSI. And thank you very much to Ibu Dr. Engineering Nurdiana Bintu Nurdin for insightful and comprehensive lecture about heterocyclic chemistry and its role in drug discovery or medicinal chemistry. Your expertise and clear explanation have greatly enhanced for our understanding of this field. Ladies and gentlemen, now we come to the end of today's agenda. We will take a moment of photo session. The photo session will be guided by Rohman. For Rohman, time is yours.
Okay, please cover your camera. Okay, 1, 2, and 3. Again, 1, 2, 3. Thank you.
Thank you very much for Rohman and all of the participants in the photo session. Before we part way, I want to remind next lecture about disparity of bioactivity natural product with Bapak Dr. Antonius Heri Cahyana from Universitas Indonesia and will be moderated by Bapak Dewangga Oki Bagus, SSI, MSI, PhD. So, please make sure to join us at the same time on Thursday. Thank you very much for your kind attention. Have a great day and wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much. Have a nice day.
Salam. Thank you very much.
Thank you.
Have a nice
Have a
day.
great
Thank
day.
you.
Thank you.